All right, so today we're taking a deep dive into something pretty wild.
Yeah, definitely out there.
We're talking about using the immense gravity of black holes, literally warping the fabric of space-time to maybe, just maybe, push beyond what Einstein told us about gravity. We're going to use his predictions of how light bends around massive objects, that's gravitational lensing, to test these limits. Black holes are the perfect lab for this.
It is pretty incredible when you think about it. I mean, Einstein's general relativity, GR, as we call it, it's been a rock star theory. It's explained so much about the universe.
Wow.
There's a but.
Right.
It kind of hits a wall when we try to mesh it with quantum mechanics, that whole world of the super tiny.
Like they just don't talk to each other, those two theories.
Exactly. And that's where things get exciting.
Yeah.
Because physicists have been trying to figure out what happens if you sprinkle in some quantum corrections to gravity itself. This leads to all sorts of mind-bending theories like string theory and loop quantum gravity. We're going to focus on one called effective quantum gravity, or EQG for short.
Snappy. So EQG, it's not about ditching Einstein completely, right?
No, it's more like adding an extra layer, especially when it comes to these, behemoths of the cosmos, black holes.
These cosmic monsters.
Yeah. So in the papers we're looking at today, they dive into two ways these quantum corrections could play out in static, non-rotating black holes. Just to keep things simple, we'll call them Model 1 and Model 2.
Okay, I'm with you.
Both models have a mass, that's your standard m, and then they introduce this new parameter, a quantum parameter, we'll call it zeta.
Zeta, like the Greek letter.
Yeah, exactly. And it basically tells you how quantum-y this black hole is.
How strong those quantum effects are, basically.
Yeah. Now, the cool part, when zeta is 0, both models, poof, they just become your regular run-of-the-mill Schwarzschild black holes, Einstein's classic.
Back to the basics.
Exactly. So what gets interesting is how this zeta parameter shakes things up. Model 1, for instance, it can actually have a double horizon.
A double horizon. Okay, you're losing me a little.
Right, so imagine a black hole's event horizon, that point of no return, the boundary you can't come back from.
Yeah, got it.
Now picture this. Model 1 can have another horizon, another point of no return inside that first one.
So like a black hole within a black hole.
Kind of. It's a really bizarre consequence of these quantum corrections.
Yeah.
Model 2, on the other hand, it just has a single horizon, but it's kind of squished compared to a regular black hole.
All right, so double horizon, squished horizon. These quantum corrections definitely mess with the classic black hole picture. So our mission today, if we choose to accept it, is to figure out how these quantum quirks in both Model 1 and Model 2 could change how these black holes bend light, how they act as these cosmic lenses.
Exactly. Like how does this quantumness, if you will, change the game of gravitational lensing?
We'll focus on supermassive black holes since they're the real heavy hitters, and they do the most extreme lensing, like Sagittarius A, the one at the heart of our very own Milky Way galaxy, and of course, M87, the one we saw in that incredible first ever image of a black hole.
Oh yeah, that was amazing.
We'll also see what clues we can get from the Event Horizon Telescope data, that's what gave us that image, to try and pin down those quantum effects. So let's get down to brass tacks. How do these quantum corrections actually change what we might see out there in the universe?
Okay, well, here's the thing. Surprisingly, the photon sphere, this region around a black hole where light can actually orbit.
Wait, light can orbit a black hole?
Oh yeah, that's the photon sphere. And get this, it stays the same in both models, doesn't budge no matter what zeta is, just like Einstein predicted.
Okay, so some things stay the same.
Exactly. But the way light bends around the black hole, that's where things change. We call that the deflection angle.
In this deflection angle, this is where we start seeing those quantum fingerprints.
Bingo. We can even define these quantities, strong lensing coefficients, we call them, that describe how strongly the black hole bends and distorts the light.
So like a measure of how warped those images get.
Precisely. And here's where Model 1 throws us a curveball. Our sources say that for Model 1, these coefficients, they actually decrease as zeta increases. So the more quantum-y the black hole is, the less it warps the light in a way. Regular black holes, they have these fixed values for these coefficients. Model 2, though, it pretty much stays put, doesn't really change with zeta like it's sticking to Einstein's script.
Interesting. So Model 1 is the rebel, the one messing with the established norm.
Exactly. Now, if we translate this to what astronomers actually observe, these changes in Model 1 could mean that for supermassive black holes, the positions of those lensed images, those ghost images, they could shift around a bit. The separation between those images, that could change too. But get this, these quantum-y black holes in Model 1, they might actually make those ghost images appear brighter, even brighter than what Einstein's theory would predict.
Wait, Brighter. That seems counterintuitive. Like, shouldn't a more quantum black hole be even more mysterious, even harder to see?
You'd think so, right? But that's the beauty of these models. They
Hmm.
can lead to some really unexpected consequences. And the papers we're looking at, they actually quantify these potential changes. They say those shifts in position could be tiny, like fractions of a microarcsecond, really hard to detect. But the separation between images, that could change by tens of nanoarcseconds, which is a bit more noticeable. And the brightness, it could even double in some cases.
Double the brightness. That's huge. Astronomers would definitely notice that. What about those time delays? How the different lensed images, those ghost images, can arrive at different times.
Oh, right, the time delay. Yeah, that's another really interesting aspect. For Model 1, we see some pretty significant deviations in the time it takes for those images to arrive. For M87, the time delay between the first and second images could be off by almost 20 hours at a certain Zeta value.
20 hours? That's like a whole day difference. That's not subtle at all.
Yeah, it's a pretty dramatic effect. Model 2, as usual, it just hums along, sticking with Einstein's predictions.
All right, so Model 1 is really giving us some clear, potentially observable signatures. But how do the actual observations from the EHT from Sagittarius A and M87 play into all of this? Can they help us confirm or deny these quantum corrections?
Absolutely, they're crucial. We can use the size of the black hole's shadow, the dark silhouette that the EHT sees, to place some limits on that quantum parameter, zeta. For M87, the EHT data suggests that zeta from Model 1 can't be larger than about 0.9 times the black hole's mass.
So there's an upper limit on how quantum M87 can be, at least according to Model 1.
Exactly. And for Sagittarius A, the EHT data gives us a bit looser constraint, allowing zeta to be up to 4 times its mass.
So M87's data gives us a tighter limit on those quantum corrections in Model 1. Interesting.
Yeah, and it just highlights how important these observations are. They're helping us refine our theories, understand the limits of what we know, and push beyond them.
So, to recap, our deep dive has shown that those quantum corrections in one type of EQG black hole, Model 1, could lead to some subtle but potentially observable changes in how light bends around supermassive black holes. These changes affect the positions of those ghost images, their brightness, and especially the time delays between them.
And while the EHT is giving us our first tantalizing glimpses, it's still a real challenge to definitively say whether a black hole is perfectly described by Einstein's theory or if these quantum tweaks are really there. The scales we're talking about are mind-bogglingly small, and even our most advanced instruments are just barely scratching the surface.
It really makes you wonder, though. Will future telescopes, even more precise and powerful than the EHT, finally give us the evidence we need to confirm or deny these quantum corrections to our understanding of gravity? Could we be on the verge of a whole new era in physics, where we finally bridge the gap between Einstein's world and the quantum world? Definitely something to think about. Thanks for joining us on this deep dive.